For decades, scientists have believed that the universe is 13.8 billion years old. But a recent study using data from the James Webb Space Telescope suggests that the universe may be twice that age, at 26.7 billion years. JWST's infrared capabilities allowed astronomers to peer back in time to the earliest moments of the universe, and what they saw was unexpected. They discovered galaxies that were forming and evolving much earlier than they should have been, according to the standard model of cosmology. This has led some astronomers to question whether the Big Bang actually happened, or if there is another explanation for the existence of the universe. Others argue that the new findings are simply a result of our incomplete understanding of how galaxies evolve. So, how old is the universe? Is it 13.8 billion years old, as the standard model of cosmology suggests? Or is it twice as old, as some recent observations imply? Finally, and most importantly, how did galaxies in the early universe evolve so quickly into larger and more luminous galaxies? Does the age of the universe have anything to do with it? Let's find out. Currently, the Lambda cold dark matter, or LCDM model, is the most widely accepted cosmological theory for the universe. It describes the universe as an accelerating, expanding system, incorporating the presence of dark energy and dark matter. The LCDM model successfully accommodates key features of the Big Bang theory, including the cosmological redshift of light from distant galaxies. However, recent observations from the James Webb Space Telescope have raised intriguing challenges to the LCDM model. By peering into the deep universe and observing the nature of high redshift galaxies, Webb has revealed aspects of the universe that the LCDM model struggles to explain. The issue is with the redshift. Currently, the universe has a redshift of 0, and as we go back in time, the redshift goes up. This means objects at higher redshifts are farther away and represent earlier stages of the universe. Recent observations made by the James Webb Space Telescope have contradicted the traditional model of galaxy formation. The telescope has observed fully developed and bright galaxies at redshifts of Z equal to 11 and 15, which is just 300 to 500 million years after the Big Bang. These galaxy findings are surprising because they are much older than the first galaxies that were thought to form. The impossible early galaxy problem is a conundrum in cosmology that arises from the discrepancy between the predictions of the Lambda CDM model and the observations of high redshift galaxies. The Lambda CDM model predicts that stars began forming in the early universe when it was around 150 million years old, at redshifts greater than 20. This is puzzling because it would have taken these galaxies billions of years to form under the Lambda CDM model. Naturally, the Big Bang theory has been challenged by some astronomers who have questioned the occurrence of the Big Bang and wondered if there is any missing link in the star and galaxy formation mechanism. However, there is observational evidence for the existing theories, so no one knows where the science is going wrong. The simplest explanation could be the miscalculated age of the universe. Have you heard of angular size and angular diameter distance? These concepts are used to measure the distance to galaxies in deep space. If we know the angular size and the physical size of an object, we can determine how far it is, or the angular diameter distance. In everyday life, we know that as the distance to an object increases, its angular size decreases. This is because the further away an object is, the smaller it appears in our field of view. However, this principle does not apply to galaxies in deep space beyond a certain point. As we observe galaxies at greater distances, their angular size appears to decrease gradually until we reach a turning point at a redshift between 1 and 1.5. Beyond this redshift, the angular size starts to increase again. This is because the expansion of the universe is accelerating at these distances. As the universe expands, the distances between galaxies increase, and their angular sizes increase as well. The Lambda CDM model predicts that the angular size of galaxies will turn over at a redshift of 1.5. However, Webb's observations have challenged this prediction, suggesting that the turnover occurs at a redshift of more than 10. This is where the forgotten idea of Fritz Zwicky enters the scene. Fritz Zwicky was a Swiss-American astronomer and astrophysicist who is best known for his work on dark matter. He was also one of the first scientists to propose the tired light hypothesis, which is an alternative explanation for the redshift of distant galaxies. According to Zwicky, light photons lose energy through collisions with other particles during their journey to us, resulting in a shift toward the red end of the spectrum. This idea did not involve the Big Bang or the expansion of the universe. While Zwicky's idea cannot fully explain Webb's observations, theoretical physicist Rajendra Gupta has proposed a novel approach to address the discrepancy between the LCDM model's predictions and Webb's observations. He argues that the tired light hypothesis cannot fully explain Webb's observations, as it does not account for the expansion of the universe. To address this, Gupta introduces the Covarying Coupling Constant, or the CCC model, which posits that the fundamental constants of physics, such as the speed of light, Planck's constant, and the gravitational constant, are not constant in time. Instead, they undergo variations that extend the timeline of the universe's evolution. Gupta's work on the CCC model and tired light hypothesis offers an alternative to the LCDM model, which describes the universe's acceleration with a constant lambda. The CCC model introduces another constant that considers the changing evolution of fundamental constants over time. This addresses challenges of early galaxies that the LCDM model cannot explain. He investigated several models to determine which one best aligned with the observations. These models included the tired light model on its own, the combination of tired light with the CCC model, the combination of tired light with the LCDM model, the LCDM model in isolation, and an alternative version of the tired light model. Of these models, the CCC plus TL and LCDM plus TL models were of the utmost importance. The reason for this is illustrated in the following graph. The plot shows the relationship between the redshift and angular size of galaxies. The blue and red dots represent the galaxies observed before and after the James Webb Space Telescope, respectively. The different curves show how the angular size of galaxies varies according to different cosmological models. The currently accepted model, the Lambda cold dark matter, LCDM model, is shown in green. The LCDM model predicts a turnover in the angular size of galaxies at a redshift of about 1.5. Beyond this redshift, the angular size of galaxies in the LCDM model deviates significantly from the observed values. The CCC plus TL model, shown in dark blue, predicts a different relationship between redshift and angular size. In the CCC plus TL model, the angular size of galaxies continues to decrease with increasing redshift. This model is able to match the observations of galaxies made before the Webb telescope, and it also aligns with the high redshift galaxies observed by the Webb telescope. The analysis compared theoretical models to observational data and examined physical size predictions. CCC plus TL model demonstrated an advantage in this aspect, predicting objects at higher redshifts to be 15 to 20 times larger than LCDM plus TL model. This explains the observed massiveness of high redshift galaxies, further supporting the viability of the CCC plus TL model. According to the CCC plus TL model, the universe would be 5.8 billion years old at a redshift of 10 and 3.5 billion years old at a redshift of 20. This extended time frame allows for more opportunity for galaxies to form and evolve into massive and luminous structures, providing a more favorable explanation for the observed properties of high redshift galaxies. Out of all the basic and hybrid models considered in the study, the CCC plus TL model was found to be the best at explaining the observations among the basic and hybrid models considered in the study. Its combination of the tired light hypothesis and the Covarying Coupling Constant concept resulted in a more precise match with the data. The estimated age of the universe under this model is around 26.7 billion years, which challenges previous calculations and could lead to a revised understanding of the universe's timeline. Nevertheless, science cannot be adjusted to agree with observations. There are loopholes in the hybrid theory of Covarying Coupling Constants and tired light. If the constants fluctuated in the early universe, their effects should also be evident in experiments conducted on Earth today. However, numerous experiments have provided compelling evidence for the constancy of these fundamental constants over time, up to more than 1.7 billion years. Also, if we combine the tired light hypothesis with the CCC model, it could affect the spectral characteristics of the cosmic microwave background. As scientists have conducted thorough research and measurements on the CMB, any noticeable deviations from its uniformity might be a big obstacle for the CCC plus TL model. Despite the challenges posed by the JWST to the LCDM model, astronomers are exploring alternative ideas. It'll be interesting to see which model fits best with future telescope observations. I appreciate you taking the time to watch my video. I hope you found it helpful and informative. See you next time.